So, hello students and welcome to this module about district heating, district cooling and electricity production. This is the fourth technical module, and what we will discuss today is briefly tri-generation processes. So what you will learn in this module is a little bit about the idea with cogeneration. For many of you, this module may be a bit too basic, but my experience from many years is that not everyone is familiar with the basics. And anyway, and now you must forgive my pronunciation of Latin, repetitio est mater studiorum, which means that repetition is the mother of learning. So what we will talk about is just some basic principles and as the processes are concerned. We will not go into any real details. One reason for that is that the actual process solutions will have to be adapted to the local conditions. And another reason is that I assume that you will already be familiar with the basic thermodynamics. So what we will talk about is efficiency, and then we will also briefly talk about the societal importance of proper system solutions. The example I'm talking about in this module is based on fuel-fired electricity production, and I'm also limiting myself basically to steam turbines for electricity. A few words about electric efficiency first. The electric efficiency of a fuel-based electricity production process is defined as the electric energy output divided by the fuel energy input. Now there's a problem, because the fuel energy may be based on what is known as the lower or the effective heating value, or it may be based on the higher or the calorimetric heating value. You should know these two terms from before. And as you know, may the difference between these two values be significant. I'm used to the lower heating value because that is what we use in Sweden, and it's also quite common in Europe, but it may be different in your country. But what I will say in this module is all based on the effective heating value. In case you feel insecure about these things, I would like to refer you to the links shown in the slide. They are certainly more than 10 years old, but what is said on these pages still holds. I do not demand that you learn to do the proper exergy calculations mentioned in the second reference, but what I do demand is that you understand and acknowledge the problems that may occur when people use ambiguous definitions and terms, so that you in the future will always stick to the proper terminology. So what I will talk about now is the electricity output as related to the effective heating value, and then also about the total energy output, which is not the same as the electric output. I'm using first law estimates, so there is no evaluation of energy quality. Now just to go through the simplest process. Based on the lower heating value, will most coal-fired condensing electricity production exhibit an electricity efficiency about 40 to 45%, or at the very least below 50%. The remaining part, more than half of the fuel energy, is cooled away to the sea, to a river, or in a cooling tower. The very simplest schematic for a condensing power station is what you see in this slide. And I will just point out the most important features of it. We have a boiler, the walls of which contain enclosed water at a high pressure, say 150 bar. Inside the boiler volume is the fire, and that could be burners or grate firing or gas firing or oil or whatever. So heat from the fire is transferred to the walls and heats the water to the boiling point. and then the water enters into the steam dome, which is usually above the boiler. In the steam dome is an equilibrium of steam and liquid water. The hot gases from the combustion in the boiler escape through the flue, and here I've only indicated the first parts of it. Following these first parts would be the flue gas cleaning system, the flue gas fan and the chimney. But I've skipped all that for the moment since it is not relevant for this module. To run the turbine, which in turn runs the generator, we first extract steam from the dome. But that steam is saturated, because in the dome there is an equilibrium at the boiling point, and the boiling point is set by the pressure. So if we assume 150 bar, then the boiling point is about 340 degrees Celsius. Now, we do not want to have saturated steam coming into the turbine. So the steam is superheated prior to the turbine inlet. This is achieved by letting it meet the hot gases from the combustion chamber. So the steam tube runs counter current to the hot gas in the upper end of the flue. So when the steam enters the turbine, it may be about 600 degrees, but it will still have a pressure of 150 bar. In reality, will there be a set of turbines, and there will be crossovers and side streams of steam and intermediate heating, but in this schematic I have omitted all such details. So following the turbine is a condenser, and to this condenser is fed cooling water. This water may come from a lake or from a river or from a cooling tower or from the sea or something. The colder the cooling water, the better. The condensed steam, the condensate from the condenser, now has a low pressure and a low temperature, maybe 10 degrees Celsius and a mere fraction of atmospheric pressure. So through a set of pumps is the pressure raised back to 150 bar, and then the water is preheated in a set of heat exchangers and returned to the boiler walls for another round. The maximum amount of electricity is set by the difference between the steam pressure and temperature at the turbine inlet and the pressure and temperature in the condenser. This is equivalent to the enthalpy difference between the inlet and outlet of the turbine. So to maximize electricity efficiency, you want to have the coldest possible cooling water to the condenser and the highest possible pressure and temperature at the turbine inlet. But there are limits. The higher the steam pressure and temperature, the more severe becomes the corrosion problem inside the steam superheater tubes and in the turbine. So in most cases is the pressure only about 150 to 160 bar, and the temperature is only about or below 600 degrees. And there may be other limitations. If the combustion gases contain corrosive components like chlorine or sulfur compounds or vanadium or such, then will the corrosion from the outside of the superheater tubes be part of the limits. So we have the steam corrosion from the inside and the eventual corrosion of flue gas components from the outside. So for the practical reasons just mentioned, will the limit of the electricity efficiency based on the lower heating value be around 40, 45, maybe 50%. Since there is only one product, electricity, will the total efficiency be the same as the electrical efficiency? So based on the higher heating value, would the corresponding numbers be reduced by some 5, 10 or maybe a bit more percent? Anyway, more than half the fuel energy is simply lost in the cooling water. So what happens when we introduce district heating is that we use the district heating water to cool the condenser after the turbine. But the return temperature from the district heating network will always be higher than the cooling water temperature we might use when using river water or cooling towers. Again, is the tubing, of course, more complicated than I show here, but what I try to illustrate is that you want to use the return temperature from the district heating system to set the temperature in the condenser after the turbine. And you want to do that to maximize the electricity efficiency. So the lower the district heating network return temperature, the higher the electricity efficiency. But the electricity efficiency will always be lower than what can be achieved in condensing mode. The positive thing with this case is that the heat losses from the condenser have now been turned into a commercial product. So you lose a bit of electricity, but you gain a new product. And that will in turn improve the total efficiency. Introducing an absorption heat pump in the system to co-produce cooling will further reduce the overall electric efficiency, since the heat pump actually needs a bit of electricity for its operation. So the electricity output from the plant will be slightly reduced. But now you will have a product mix of 3 products to sell. Basically, will the total efficiency be about the same in trigeneration as in cogeneration. So what happens is that you sacrifice a bit of electricity production, but you gain total efficiency. And also, when introducing district cooling, you will reduce the demand of electricity among your customers, because they no longer have to use local air conditioning units. So even though the central plant may produce slightly less electricity, will there most likely be a positive net effect for the city as a whole, so that the total demand of electricity for the collective is reduced. In the case of cogeneration, district heating and electricity only, will the electricity production be very weather dependent. On cold days, when district heating is demanded, will you be able to produce lots of electricity? But on hot days, when the demand for district heating is low, will you not be able to produce very much electricity, if any at all? But with a trigeneration system, it's completely different. On cold days, you do not care to produce cooling, so that's just like cogen. But on hot days, people want to have cooling. And to produce the coolant, you use the district heating water. You just do not send the district heating water to the customers. You use it internally for cooling production. But since you produce it, you can also produce electricity. Then it must also be recognized that CHPC plants, combined heating, power and cooling production, CHPC plants will typically be smaller than the condensing power plants. This is also a natural consequence of the fact that district energy systems, for robustness, for flexibility and redundancy, will include several production units. As a result of the smaller size and the higher number of plants, will such systems be more labor-intensive. So local jobs are created because the production units are placed close to or inside the city. And then can the local production units also play an important role in the local or regional waste management system. And that is because different production units may be using different fuels. And that, in turn, will add to system stability, to system security, and to a sustainable energy system.